Hi everyone, this is going to be a two-part lecture on a technique of integration called decomposing a rational function into partial fractions. So first, let me explain what a rational function is. If you look at the word rational, you'll see the root word ratio. This means a ratio of polynomials. For example, you might have something like 2x plus 2 over x squared plus 6x plus 8. There, the numerator and denominator are both polynomials, and so we have a ratio of polynomials. This is a rational function. We use this technique of integration when we're looking at our denominator and we realize that we can factor it. So for this particular example, this denominator would factor as x plus 4, x plus 2. Okay. Then what we do is we take the original rational function that we're working with, and we're going to break it into smaller rational functions. So we'll see examples. I'm not going to write out anything. In fact, we're going to work with this example in just a minute. But the idea is you want to take something large and break it into smaller pieces, which might be easier to integrate immediately. Then, again, we'll see examples. We'll basically come up with an expression that allows us to solve for the numerators of our decomposition. And what we'll do is we'll just match like terms. So next, we're going to look at some examples. And in this particular lecture, all examples are going to have the property that when we factor the denominator, no term is repeated. So for example, I'm not going to see something in this lecture like x plus 4 times x plus 2 squared. So no repeated factors in this first video. And then in the follow-up to this lecture, we will look at expressions where you have repeated factors, or maybe you don't have this property met originally where your numerator is a lower degree than the denominator. So that will be in part 2. Okay, this is the rational function that we just mentioned on the first slide. So in this particular integral, I've gone ahead and written the denominator in factored form. So that allows us to jump straight to the breaking apart into smaller pieces and using the method of equating coefficients that I mentioned. I think what I will do is do the decomposition into partial fractions down here. It's kind of a calculation you do off to the side, if you will. And then I'll return up here to finish the integral. So at the end, it's going to look like the first work is at the bottom and then the ending is at the top. Okay, so here's what we're going to do is we're going to take our integrand and write 2x plus 2 divided by x plus 2, x plus 4. Then I have here two distinct factors, both appearing only once in the denominator. So again, no repeated terms. These are both first order factors, meaning I just have plain old x, I don't have x squared or anything like that. To break apart such an expression, I'm going to say that this fraction can be rewritten as something over x plus 2, we'll call that something a, plus something over x plus 4. What I've done here is backwards to what we usually do with fractions. So often we start with two separate fractions and we say, hey, what's their common denominator so that we can put them together into one? Here we're going the other direction. I'm saying, hey, imagine that we found a common denominator and put two things together. What could they have looked like? So here it's like, imagine you started with this and you wanted to actually add these together. You would say, okay, well, that's going to mean my common denominator is the product of these two denominators. So that's x plus 2, x plus 4. I have to do a times this one, so a times x plus 4, plus b times x plus 2 in order to get my new numerator. And then that sum is going to be over the new common denominator. So from this line to this line is what we usually do with fractions. We usually start with multiple fractions and we put them together into one. Okay, now we have this equality saying 2x plus 2 over this common denominator equals this numerator over the common denominator. So some of what I've written here will be skipped in future computations, but you can imagine multiplying both sides of this equality now by the common denominator. So let's cancel out the denominators. We'll just be left with equality between the numerators. So in particular, on the left, we have 2x plus 2. And on the right, this numerator, I'm going to go ahead and distribute ax plus 4a plus bx plus 2b And then I like to group like terms in terms of x. So let me put ax and bx together. In fact, we could write a plus b times x, and then plus the constants. So plus 4a plus 2b. Okay, take a look at that. Now we are ready to equate coefficients of similar terms. What that means is that we're going to look at the constants, and we'll say this constant expression, so no x here, must be equal to this constant. And similarly, this expression that has x must be equal to this expression, which also has x. To see why that would have to be true, you could think about plugging in x equals 0. You would be left with the constants are equal. And then if the constants are equal, everything else has to be equal. So that's how you can justify this approach. Let me start with the constants. I have 2 equals 4a plus 2b. I'll write that out, and then I'll divide everything by 2. So this is equivalent to 1 equals 2a plus b. All right. Then the second equation we get relating a and b is going to be a plus b equals 2, where it's this 2 right here, the coefficient of the x term. So from over there, we also know that 2 equals a plus b. This kind of pair of equations, or for something bigger, might be a triple of equations or something like that, but this set of equations for your unknown numerators is where you usually end up with in a partial fractions problem. So at this point, you have to know how to solve a system of equations for unknowns. In this case, we have 2 equations for 2 unknowns. The typical ways to solve those by hand would be to use substitution or elimination. If you're good with matrices, especially if you have a larger set of equations, you might set it up as a matrix problem. Looking at this pairing, because I have b and b, and I've even stacked the equations vertically like this, I'm going to use elimination, which means I'm going to take the second equation, and in this case, I'm going to subtract it from the first equation so that my b's cancel out. I'm worried that I'm going to run out of room, so let me do that subtraction, but I'm going to write it over here so that you can actually see it. So the idea is I want to add or subtract a multiple of one of the equations to the other in order to wipe out one of the variables to reduce down to a simpler problem. So in this case, we're going to do 1 minus 2 is negative 1. 2a minus a is just 1a, and then b minus b is 0. So this tells us a equals negative 1. I'm just going to basically rewrite that. And then once we know a, we also know b, because it was the case, if you look inside these parentheses here, that a plus b equals 2. So we can say b equals 2 minus a. So that's going to be 2 minus negative 1, which is 3. Okay, let me pause for a second and let you work through this computation if you haven't already finished it. So elimination is what I did here. If you'd like, you could also try substitution. And then when I come back, I'm going to take this integrand and rewrite it now using this partial fraction decomposition. It's going to allow us to immediately integrate this expression by hand. Before I move back to the integral, let me do one more thing, which I normally skip when I'm working these out by hand, and that is return to this line here, where we originally took our expression and broke it into smaller pieces. And let me just explain what's happened. We can now say that 2x plus 2 divided by x plus 2 times x plus 4 can be broken into smaller pieces, where the first piece looks like negative 1 over x plus 2, and the second piece looks like 3 over x plus 4. Let's just check that this is correct. So what happens now if I add these together? I would get negative x minus 4 plus 3x plus 6 all over their common denominator, which is the product x plus 2 with x plus 4, product of those two terms. Okay, if I simplify the numerator now, I get 2x plus 2, and that does agree with where we started. So this is an equivalent expression for the integrand. It's the same integrand now, it's just easier to work with. So let's go ahead and do that. What I had up here was the antiderivative of 2x plus 2 divided by x plus 2 times x plus 4. This is now equal to differentiating the sum, negative 1 over x plus 2 plus 3 over x plus 4. I don't always put sums like this inside of parentheses in integrants, but you certainly can. Let me do dx like that. Okay, we're integrating this whole expression. Both of these is an antiderivative. We know immediately it's the natural log expression. So this is going to be, let me write it to the right, negative 1 times the natural log of the denominator. We'll use absolute value to be most general. So negative 1 times the natural log of the absolute value of x plus 2 plus 3 times the natural log of the absolute value of x plus 4. For me, this is typically enough, but let me just mention properties of natural logs here, and I don't want to make this board too busy, so let me erase this extra step we did. Okay, so this would normally be fine, but I just wanted to bring back natural log properties in case it's been a while since you worked with this kind of expression. These leading coefficients can become exponents of what's inside the natural log. So this is natural log of x plus 2 to the negative 1. It's still absolute value. Sorry. And this will be plus natural log of x plus 4. I'm really struggling with my parentheses versus absolute value expressions, but that's x plus 4 cubed. And then the sum of two natural logs is the natural log of their product. So I'm going to write this all in one go as natural log of the absolute value of this cubed times 1 over x plus 2. So let me write over x plus 2. I forgot something at each point, and that was that this is a indefinite integral, so should have been picking up a constant of integration along the way. So here's the antiderivative of 2x plus 2 over x plus 2 x plus 4. Again, typically I would write this first line, but I just wanted to point out this alternative version of it. In this example, let's find the partial fraction decomposition for this rational function. So this is negative 2x squared plus 7x minus 16 all over x cubed minus 3x squared minus 4x. We're going to find the partial fraction decomposition for this with the idea that we're going to integrate it in a minute. So we'll find the antiderivative for this rational function. This denominator here is a cubic polynomial, and such a polynomial can be very hard or basically impossible to factor by hand unless there's some kind of trick or something special about it which is happening. So we will see examples of this. In this particular denominator, notice every term has an x. So we will pull the x in front of the cubic, and that's going to take it to a x times a quadratic, which we can factor by hand. So if you're doing a partial fraction problem, ideally you can factor the denominator. Okay, so we have x cubed minus 3x squared minus 4x. Okay, that's our starting denominator, but now we'd like to factor it. So I can write this as x times x squared minus 3x minus 4. And then, let's see, negative 4, positive 1. So we'll write this as x times x minus 4 times x plus 1. Okay, so that is the factors that we have for the denominator. Now let's write the expression that we had when we set up our unknown coefficients, our unknown numerators, if you will. So I'll do negative 2x squared minus, let's see, plus 7x minus 16. Okay, there's a lot going on here. All of this over, how about x times x minus 4 times x plus 1. Okay, that's our starting expression. We are going to break this into 3 separate fractions now, where each one has one of these terms as the denominator. So x minus 4, and x plus 1. each of these denominators is degree 1, nothing quadratic or higher. So the numerators for such denominators are just plain old constants. So we'll do A, B, and C like that. I am going to omit the step I did on the previous example where I kind of rewrote everything and imagined trying to add these three together using a common denominator. Let me go straight to the numerator comparison. So I'm going to say that I've gone ahead and multiplied both sides of this equality by this common denominator. In doing so, I'm left with just the numerator. So negative 2x squared plus 7x minus 16 times each of these numerators multiplied by what they would need to pick up in order to be put into the common denominator form. So a has already got x in the denominator. I need to take a and multiply it by x minus 4 and x plus 1. So the numerator I would put together if I tried to add these three together would be a times x minus 4, x plus 1, b times x plus 1, plus cx times x minus 4. Okay. Now what I would like to do is gather like terms together here. So let me, actually, I'll do this in two steps. So first I'm going to say this is a times x squared minus 4x plus 4. So x squared minus 3x minus 4, rather. Did I do that right? X squared, this one. Yes, okay. And then plus b times x squared plus x plus c times x squared minus 4x. Okay. Now let's gather the quadratic terms together, the first order terms together, and the constants together. So for the quadratics, I'll write x squared up front. We have a plus b plus c. Then for the first order term, I have negative 3a plus b minus 4c. And then for the constant, I only have a negative 4a. Okay. So at this point, I have imagined taking these three fractions and adding them back together. What would that involve? It would mean finding their common denominator. Well, we already have that on the left. And then taking the numerators and pairing them with the right denominators, the denominators they're not sitting over, so that our numerator on the right-hand side would take this form, expanded and kind of collected like forms, so that we can now match terms based on what type of x or constant they're situated with. Okay, let me give you a few seconds to write down the equations for the unknowns a, b, and c. You should end up with 3 equations for 3 unknowns. All right, here's what you should get. I'm going to start with the constants because this expression is the easiest. So we'll pair up this constant with that constant, this x term with this whole x term, and then this quadratic with this quadratic. Okay, so hopefully I'm not squeezing too much in the bottom left here, but when we pair up the constants, we get negative 16 equals negative 4a. So happily, we can immediately solve for one of the coefficients. So we know that a is 4. That means everywhere I have a in my other statements, I'm going to go ahead and put in 4, just to reduce the complexity from 3 variables down to 2. For the other 2 equations, I'm going to write them over here and switch colors so that the board doesn't get too crowded. Whenever I do partial fraction decomposition, I'm doing it on paper, say it's like a very vertical computation. And here I'm trying to work down and also left to right. So hopefully you can see this. If I now write that 7 is negative 3a, which is going to be negative 12 actually, plus b minus 4c. So 7 is negative 12 plus b minus 4c. Okay. Then for the quadratic term, negative 2 is 4 plus b plus c. Let me rewrite these, putting all the constants on the left-hand side. So I'll keep going down. I'm going to rewrite both pairs as negative 19 equals b minus 4c. And then negative 6, yes, negative 6. No, sorry, this should have been positive 19. Okay, clean that up in a second. Negative 6 is b plus c. Okay, this pair of equations is perfectly set up now for elimination because if I take the first one and subtract off the second one, the b's are going to cancel. So we'll have minus 25, so 19 minus negative 6 equals b minus b, that's 0. Negative 4 minus c is negative 5c. So overall, c is negative 5. And then the second equation is probably the easiest to work with. B is negative 6 minus c, so negative 6 minus negative 5 is negative 1. All right, let me just put those numbers here so that we see what the partial fraction decomposition looks like. A was 4, B was negative 1, and C was negative 5. I'll step aside for a minute, and then we will write down the antiderivative of this rational function. That's what we start with. But now we're saying it can be written as 3 much smaller pieces, which we can immediately antidifferentiate. Typically, when you integrate a rational function like this using partial fraction decomposition, the bulk of the work is getting that partial fraction decomposition. Now, after all that we just did, we're left with 3 terms which we can immediately antidifferentiate. So let me say that the antiderivative of 4 over x is 4 natural log of the absolute value of x. So that's for the first one. Then minus, let's see, just natural log of x minus 4. That's for the second one. And then for this third one, it's going to be minus 5 natural log of x plus 1. And this time, I did not forget my constant of integration. This is correct. At this point, we're basically done. But just to review properties of natural log, let's write this as one giant natural log. So this is going to be numerator, denominator, denominator because of the subtraction. So natural log of a minus natural log of b is natural log of a over b. Then this is going to become an exponent. This is going to become an exponent. So we're going to get natural log of x to the 4th all over x minus 4 times x plus 1 to the 5th plus our constant of integration. Now let's find the partial fraction decomposition for x to the 4th minus x squared plus 1 all over x to the 5th plus x so that we can eventually antidifferentiate that rational function. Here, our denominator is not too busy. We have x to the 5th plus x. All I can do is factor out an x. So that leaves us with x times x to the 4th plus 1. If you actually plot this degree 4 polynomial, it has a y-intercept of 1, and then it opens up. So it doesn't have any roots or anything like that that cross the x-axis. So we'll leave x to the 4th plus 1 as it is. So now we can say that x to the 4th minus x, minus x squared, sorry, got turned around for a second there, x to the 4th minus x squared plus 1 all over x times x to the 4th plus 1 can be decomposed into 2 expressions whose denominators look like x and x to the 4th plus 1. Going to need a larger numerator for that. This first one is the kind of expression that we've been seeing. So for this first numerator, I'm just going to put a constant a and we'll solve for a. For this second term, the degree of the denominator is 4. Here's what you want to do when you're looking at a denominator in a partial fraction decomposition whose power is higher than 1. You want to write the most general polynomial expression that you can for the numerator whose degree is 1 less. So in particular, 1 less than x to the 4th, 1 degree less would be x cubed. So my most general cubic polynomial would be bx cubed plus cx squared plus dx plus e. So I'm going to have 4 unknowns, b, c, d, and e associated with this second piece. Then the rest of it's going to be the same, where we imagine that if we paired up this numerator with this numerator with this denominator, in order to get to x times x plus 4, x to the fourth plus 1 as a common denominator, we would then say, well, the numerators must be equal. So let's do x to the fourth minus x squared plus 1 equals, you can go ahead and distribute a to this denominator. So we'll have a x to the fourth plus a. And then similarly, let me distribute this x to these 4 terms in my second numerator. So we will have b x to the fourth plus c x cubed plus dx squared plus ex. Okay, there's not a lot in common here. The only terms I have in common are the x to the fourth terms. So we have fourth order terms, third order, quadratic, first order, and constant. Let me set up those equations here. I'll switch to orange. For the for the degree 4 terms, we have 1 here, so 1 x to the fourth on the left equals a plus b on the right. Okay. Then here we have 0 x cubed. So my next degree will be 0 on the left. Then we just have c here. So we know nicely right away that c is 0. Then we have negative 1x squared on the left. And the only x squared term we have on the right is this d here. So we also immediately know what d is. And then I'm on first order, linear. We don't have one of those on the left. So again, on the left-hand side of this pairing, I'm going to write 0. And on the right-hand side, e. And then for constants, we have 1 on the left and just a on the right. Okay, so we immediately know that this is 0, this is negative 1, this is 0, this is 1. I just have to solve for b. b is 1 minus a, so actually that's also 0. So this turned out to be not too complicated. I secretly did that on purpose because we're going to have even more examples to finish this lecture and in the next lecture. But I wanted to highlight with this example before we move on that sometimes you have a higher degree in your denominator than what we've seen so far. Still set it up the same way, same principle, except your numerator needs to incorporate more terms. So for a fourth order polynomial denominator, you have a cubic numerator. We'll see more examples like this in a minute, but until we do, let's go ahead and finish this problem. So given this partial fraction decomposition, let's anti-differentiate the rational function that we started with. Thanks to the partial fraction decomposition we just did, we know that this rational integrand on the left, x to the fourth minus x squared plus 1, all over x to the fifth plus x, can be rewritten in terms of smaller and easier pieces, 1 over x plus negative 1x over x to the fourth plus 1, where this negative 1 here was the coefficient d that we solved for. We can anti-differentiate each of these individually. The first one is immediate. That's just natural log of the absolute value of x. For the second one, you could try, say, a trig sub, if you think of the denominator as x squared plus 1. I actually think it's easiest with a u sub. So let me have u equal x squared. This one's not obvious, so if you didn't see this, that's okay. Let u be x squared so that du is 2x dx. And if you'd like, you could write that as negative 1/2 du is negative x dx, because those are exactly the terms that we see in that expression on the right. Now I'm going to go ahead and anti-differentiate the first one, kind of peel that off. It's going to be natural log of the absolute value of x. And then how about minus 1/2 antiderivative of 1 over u squared plus 1 du. Take a look at that and see if you recognize how to anti-differentiate this expression. This antiderivative we can recognize because 1 over u squared plus 1 is the derivative of arctan of u. So we can finish this up now and say that the antiderivative of our starting integral is natural log of the absolute value of x minus 1/2 arctan of u. But because u is x squared, let me write arctan of x squared plus a constant of integration. Let's finish this lesson with this example. So we would like to find the partial fraction decomposition of this rational function, so 8x squared minus 5x plus 23, all over x cubed minus 2x squared plus 5x minus 10. So the denominator is a cubic polynomial, which means that trying to factor it is not as routine as, say, a quadratic, but there is something that we can do here. So let's take this denominator, x cubed minus 2x squared plus 5x minus 10. And what I'm going to do is notice that the first two terms have a GCD of x squared, whereas the latter two terms I could factor 5 out. Just try it, see what happens. So when I do that, I'm going to write x squared times x minus 2, then plus 5, also times x minus 2. But now it's like I can factor an x minus 2 out of each of these terms. So I have two terms, and they both have an x minus 2 in common. So I'm going to write x squared plus 5, this quantity, times x minus 2. This is a factorization of our cubic denominator. Again, we can't take this any further. Similar to that degree 4 example we saw earlier, this is a first order term. That one's done. This quadratic opens up with a y-intercept of 5. So no more factoring there. Also, it's just kind of obvious. So this is the end of our first step in our computation. So next, what we want to do is take our original expression, so 8x squared minus 5x plus 23, all over this denominator, x squared plus 5 times x minus 2, and actually probably bump into this. Let me write the degree 1 term first. With this expression, we know we're going to have something that looks like a over x minus 2. For the second factor in our denominator, it's quadratic, x squared plus 5. That means that the general numerator is going to be 1 degree less than this. So I want to write the most general degree 1 expression I can. That would be bx plus c. So you want to have your numerator be a polynomial whose highest order is 1 less than the denominator. Now let's imagine we do the kind of putting these back together part. So I'm going to take this numerator, 8x squared minus 5x plus 23, and set it equal to ax squared plus 5a. Then plus bx squared minus 2bx minus 2b minus or plus cx minus 2c. Okay. Let me pause here, check my work, start grouping like terms together. Now I'm going to start setting up the system of equations. We are going to have 3 equations for 3 unknowns. Let me first do the constants. On the left, we have 23. On the right, we have 5a. So this is going to match with this and this, minus 2c. Okay, so that's our equation associated with if we plugged in x equals 0. Next, let's do the x terms. We have negative 5x, so negative 5 on the left, and then negative 2bx plus cx. So how about negative 2b plus c? And then for the quadratics, we have 8x squared, so 8 on the left, and then a plus b, and that's it. Okay, so we have this system of 3 equations for 3 unknowns. It's not the nicest. Nothing immediately got solved for. There's also no immediate elimination. And that, like, I have negative 2c, but then just c, 5a, and then just a, negative 2b, and then just b. But we can still work with this. We can set up an elimination. Let me take the second equation and multiply everything by 2 so that we get negative 10 on the left and then negative 4b plus 2c on the right. Now I have 2c here and a negative 2c there. So let's pair this up with the first equation. We'll add these two together and we will cancel out the c terms, leaving us with a combination of a and b. So when I add these two, I get 13 equals, the c's cancel, 5a minus 4b. Okay. Now we have an equation with a and b and another equation with a and b. So let's partner those up. Guess we could take the first equation and multiply everything by 5. Okay, so over here, I'm going to take this equation, multiply everything by 5 to get 40 is 5a plus 5b. Okay, so that is this equation times 5. Let's subtract this equation from it and hope that the numbers, I'm not making an algebra mistake. So how about I'm going to write negative that equation. 13 equals 5a minus 4b. This way the a's will cancel. Okay. 40 minus 13 is 27. And then 5b minus negative 4b is 9b. This implies that b equals 3. We got one. With this, find a and c. All right, let's check your work and also mine at the same time. So hopefully we agree. B is 3. Here's a pretty simple equation relating a and b. So from that equation, 8 equals a plus b, I can say that a is 8 minus b. So that's 8 minus 3, which is 5. All right. And then c, let's go back to this one. C is going to be negative 5 plus 2b. 2b is 6. So negative 5 plus 6 is 1. Pretty nice numbers, actually. Okay, we are going to anti-differentiate this in a second, but before we do, let's just summarize that a was 5. So we'll see 5 over x minus 2. And then this numerator is going to have 2 terms this time. It's going to be 3x plus 1. Okay, so we will now anti-differentiate this. All right, we're now ready to say what the antiderivative of our original rational function is. We have it in terms of smaller pieces. The first one, 5 over x minus 2, is ready to go. The second piece, what I'm going to do is break those into 2 separate integrals. Each one will get a technique of integration. Okay, so let me just go ahead and anti-differentiate the first one. The antiderivative of 5 over x minus 2 is 5 times the natural log of x minus 2. Okay, that one's done. Then let me say plus 3 times the indefinite integral of x over x squared plus 5 dx. So that's that first term in the second expression. And then plus 1 over, I don't know why I factored the 1 out. Okay, 1 over x squared plus 5 dx. Okay. So unlike some of the examples we've seen, these are not immediate, but they're still much, much easier than what we started with. For the middle one, let's do a u substitution where the denominator will be u. So if u is x squared plus 5, du is 2x dx, and that will take care of the x in the numerator. If you want, you can do 1/2 du, write it like that. Now it looks like an x. Let me just say 2, and I canceled it out. Okay, never struggled so much trying to write a du expression, but there we go. This one is another arctan, but in case you don't see it, let me set up this second expression here, the second one remaining, using trig substitution. We'll get to arctan that way. So here, I'm going to draw a right triangle. That's supposed to be a right angle. It doesn't really look like it. Theta will be our new variable that we'll integrate with respect to, and that will be this angle here. I have a sum of perfect squares. I'm going to put x on the opposite side. And when I said perfect square, you have to think of 5 as the square root of 5 squared. So this side will be square root of 5, so that this, the hypotenuse, is x squared plus 5. Okay, so there is the right triangle for this trig substitution. Next, let's write down our SOHCAHTOA. So we have sine of our new angle, our new variable, theta, is x over the square root. Cosine of theta is adjacent over the square root, so that's square root of 5 over the square root of x squared plus 5. And then the nice one is tangent. Tangent of theta is opposite over adjacent, so that's x over the square root of 5. That tells us that x is square root of 5 tan theta. I don't know why I can't write square root of 5. I'm struggling with my 5s. Square root of 5 tan theta is x, which means that dx, the differential in our starting integral right here, will be square root of 5 secant squared theta d theta. Okay, so sorry if I put all that too far to the bottom right. Let's keep going here now. So we'll stick with our 5 natural log of the absolute value of x minus 2. Then we're going to have plus 3 halves times the indefinite integral of, because I pulled the 1/2 out, x dx is just du, 1 over u du. Like that. Okay, that's the first two. And then plus 1, I think I'll leave that off this time, plus the indefinite integral of, notice the integrand that we start with looks like cosine divided by the square root of 5. Like that. Squared. Okay, so I've got 1 over the square root of x squared plus 5. If I square that, I get back exactly my integrand. So the integrand here should be 1/5 the cosine function squared. Dx will get replaced with square root of 5 secant squared theta d theta. Like that. Cosine squared and secant squared are going to cancel. So if we take this down the next line, we have 5 natural log of the absolute value of x minus 2 plus 3 halves natural log of the absolute value of u, but let me go ahead and put in x squared plus 5. That quantity is always positive. You don't need absolute values, but I'll just leave them. Plus square root of 5 over 5, or if you like, 1 over the square root of 5. The indefinite integral of d theta, because the trig terms canceled out. We are almost done. One more line should do it. So we have 5 natural log of the absolute value of x minus 2 plus 3 halves natural log of x squared plus 5 plus 1 over the square root of 5 theta. So the antiderivative of 1 d theta is just theta. But theta I can solve for using this relationship between x and theta. Theta is arctan of x over the square root of 5. And then plus our constant of integration. Sorry about the crowding here. So this antiderivative is a version of arctan, and here's what that looks like. Okay, so this wraps up our last example of partial fraction decomposition, but we do have a part two, so be sure to check that out.